to the last presentation for today. I will present our approach and tell you a little bit in general about our view of these problems. The work done by Theo Vincent and myself. So just to briefly introduce our group, we basically started this division of German Research Center for Artificial Intelligence in Darmstadt last year, and currently we have 40 members working on systems AI for robot learning, where we basically cover the kind of spectrum of tasks starting from low-level control up to language conditioned visual motor control, focusing on learning, robot learning, reinforcement learning, and manipulation tasks. So today I would like, we have seen, shall we say, model-based approach, then we saw an actor critic. Now it's time for the value-based approach. And I want to tell you a little bit about our recent work on coming up with something better than DQN. So the algorithm is called iterated DQN. And to describe it properly, I want to first introduce some notation and visualization, and then we'll get into it. All right, so reinforcement learning loop that we all know and love. Now, the key object, if we talk about reinforcement learning, is of course the action value function, the Q function, which is the sum of rewards under a certain policy. And once we have the Q function, then the policy is given just by taking the argmax of the Q function. Now, the key player in the theory of reinforcement learning is this Bellman operator, denoted by gamma, which acts on Q functions. And Q function is defined as the stationary point of the Bellman operator. And the Bellman operator is nothing else but this expression here. So it's an expectation of the reward plus gamma max of Q. So when we apply it to Q, we evaluate this expression, and this gives us the next iteration. So at convergence, we have this equality that Q star equals gamma Q star. Very nice. So pictorially, we can see the process of learning as a kind of journey in this space of Q functions where we are trying to approximate the optimal Q function. So what we do when we are now trying to learn this Q function, we are doing it by minimizing the so-called error. Okay, this is not nice. Let me move this. Okay. So the question arises, can't we learn gamma n Q directly? Why are we always learning just one step of the Bellman operator? So if we look inside, then we realize that in order to learn even the second application of the Bellman operator, we have to expand the argument here, which will be gamma Q, and then it becomes this. So it's a kind of nested problem, and it's at first sight not straightforward. How could we learn this? So let's think about it a bit more abstractly. The first question is how to draw the space. Okay, so we want to represent these Q functions in some space, but think about Atari games. We are trying now to understand the space of Q functions. In Atari games, the state space is pixels right? So we have 84 by 84 3-channel images, and then we have actions. So if you compute everything together, then a Q function is a vector in this kind of space. So it's very high dimensional space. Therefore, we cannot represent the Q function exactly. So what we are always working with is some kind of parametric family, and we are trying to approximate that Q function Q star. And the optimization process of DQN proceeds in this way. So we have Q given by the target network, then we have Q prime as the online network, and we are updating this online network to approximate the target closer, and then slowly moving this target network together with it. So that eventually the target network and online network both come to this point, which is a projection of the optimal Q function onto the representable space. And if you have been following this space, there are a lot of variants of DQN. There is a double DQN, where you have two networks. There is, you can use n-step returns. There is dual DQN, which is changing a bit the space of Q functions. And yeah, all these combinations are possible, and they have been shown to improve the performance of DQN. And you can depict them all into this framework. Now, particularly close to our method is ensemble DQN that uses an ensemble of networks to improve the performance of DQN. Okay, now we are ready to take a look at the iterated DQN, where the idea is that now we want to have not just one online network, but multiple online networks. So it's something in between like ensemble and DQN, but with multiple online networks, what we can do is something similar to multiple shooting in optimal control. We are basically propagating this optimization forward, and then we are enforcing these kind of constraints that the points should agree. So it's a very nice analogy to optimal control here. And what we can show actually by optimizing this kind of error, we prove we can improve the performance. So just summarizing one picture, if we use iterated DQN, and it of course can be applied with different number of iterations. On the previous slide I had 5, here we have 2, we can have also 10 or so. But essentially it gives us room to look ahead compared to DQN. Yeah, in a simple diagram it would be like this, that DQN on the left has one head, and here we have k heads. Let's see this animation. So this is the process of optimization for DQN. And here is the process for iDQN. So we have online net, Q1, then Q2. Wait. Yeah, here's the iDQN. So here we have two online networks, Q1 and Q2. And they are moving forward to the respective Bellman operator here, to the updated one. So in terms of the performance, what we can show is that iDQN here in blue for k equals 5, so with 5 heads, outperforms DQN from the Nature paper, the original version. Also DQN Adam, which is quite a bit stronger than the original one. Also other baselines like C51 and REM. So important point here is that iDQN is orthogonal to all other improvements of DQN. So potentially it can be combined with all other algorithms. So the main point from our side to prove here is that if we can outperform DQN, then it's already great, but actually it also outperforms methods with three-step return and other different further improvements. So now coming back to the challenge. So basically, when the challenge came up, Theo was still in the process of working on iDQN, and yeah, we had a little bit of a short time for participating in the challenge. Therefore, our submission was only rough. We wanted to try really a value-based method. Therefore, we went for just straight DQN by discretizing the action space into 9 bins with logarithmic spacing to have a bit more actions around 0. For the reward, actually, we took the one from Chi's submission for the final submission of ours. As actually it was quite important for this challenge to have a proper reward function. And for the stabilization, we also used LQR in our solution. So the hyperparameters are more or less the default ones for DQN. And with this, we were able to achieve, like, okay, let's say in a couple of days of trying, we were able to achieve swing up on the Pendlebot. Although we didn't proceed to the real robots evaluations because I'm very concerned about these torques here. The method for sure requires some consideration, and the robustness. So okay, of course the results are not so strong. Interesting observation here was how the discount factor affects the performance. I would be actually curious to know which one did you use. But in our case, having gamma equal to 0.85 gave the performance. But if we set it higher, which in theory should allow the algorithm to look further, actually the performance becomes worse, that the system becomes unstable. So from this brief look at the problem, yeah, we observed the bang-bang control, the effect of the discount factor, and the very low robustness. Now, to actually make it work, there are a few steps required. For once, we indeed would be glad to have iDQN, not just DQN, on the RealAIGym. An actor-critic version. So the problem, one of the problems is of course action discretization. It's very not nice for real systems. Therefore, we are considering to develop an actor-critic version of iDQN. And then also we didn't test an acrobot. This would be also one of the next steps. With that, thank you for your attention. If you have any questions, I'm happy to take them now.